Hello everyone. Today I am going to discuss Vane shear test to calculate the shear strength of a soil. So already I have discussed the three methods: direct shear test, triaxial compression test, unconfined compression test. So this is the fourth and last method that I am going to discuss to calculate the shear strength of a soil. So to calculate the undrained shear strength of a soft clay can be determined by using the Vane shear test. So this Vane shear test we can perform in the laboratory also, or we can perform in the field also. So on the field we can perform this test on the soil at the bottom of drilling hole, or also we can perform without drilling hole, directly penetration of vane into the ground surface. Right? So let's discuss what are the apparatus of Vane shear test. So Vane shear test apparatus is mentioned in this figure. So the most important is this is a steel blade. So a rod of diameter 2.5 mm and height 60 mm, having a 4 thin stainless steel, that is diameter of D, that is height is 2 times the diameter. So in the shape we will see this stainless steel blade in the form of rectangular. This is connected by a rod and two blades are connected by perpendicular to each other. Then why I am saying the diameter of the blade, right? I can say like width and length, but I am saying diameter and height and length. So why I am saying the diameter, I will explain in the next slide. And what we do, the specimen of a size 38 mm diameter and 75 mm height, that is fixed in the steel pot, and this is fixed at the base of the apparatus. So once the soil specimen is fixed at the base of the Vane shear test apparatus, then this steel blade inserted inside the soil specimen, and till the top of the steel blade, should be at a depth of 10 to 20 mm from the surface of the specimen, so that both top and bottom part should be participate in the shear phenomena. So once soil specimen is set and a steel blade inserted inside the soil specimen, then we can apply the torque. So we can apply the torque at the rate of 6 degree per minute, or we can say 0.1 degree per second. Right? And we will apply the torque till the soil gets failed. So the value of torque we will calculate. We will count what are the value. So we will just take the value of torque. Okay, and that will be that we will give the that we can take the value of by using the scale. Some scale is mentioned. So what is there? What is the phenomena is there? So we will see in the apparatus. So in the top side there is a spring is fixed. So once you will apply a torque, then a spring will rotate. So what are the rotation, that angle, and what are the K? So that will give us the torque. K into theta. So theta we will calculate. So that will depend upon the various type of apparatus. So that will give us the torque. So what we are doing, we are applying a torque, and soil gets failed. Right? So what are the formula we will use? So that I'm going to derive in the next slide. So before derivation of any formula in the Vane shear test, the one assumption you should be considered, and that is a very important assumption before deriving the formula, and that is shear strength of a soil will be constant on the cylindrical surface of this steel blade and the top and bottom of the shear surface. Are you getting my point? shear strength will be constant. Suppose shear strength of soil is S. So S will be constant on the side of the cylindrical surface, on the top of this, on the top of this value, right? And the top and bottom of the shear surface, right? So shear strength will be constant. Are you getting the point? Okay. So this the cylindrical surface I'm talking about. Why I'm taking the cylindrical surface? Because the steel blades, two steel blades are attached to this rod in the perpendicular direction. Both are perpendicular to each other. So when we will start a rotation, when we will apply the torque, then soil will start to rotate. Then a steel blade we will start to rotate, and it will form a cylindrical surface by including the soil specimen. Will be a cylindrical surface. So I am talking about that cylindrical surface in which steel blade and soil both are included, right? Okay. So in this figure you can see, so there is a mention the steel blade diameter is 12 mm and height is 24 mm. The rod having height is 60 mm. Plan is also mentioned. So plan will be look like a circular, and this circular, okay. And then then a steel plate will be, two steel blade is attached to the perpendicular to each other, and their width is 0.5 mm, right? Okay. You can understand what I'm saying, like, you know, the fourth figure, the right side top corner figure. So when the torque is applied, so this steel blade it moves, and then it forms a shear surface is cylindrical surface. Shear surface is cylindrical surface, right? So whatever the torque is applied on the soil specimen, then soil specimen will resist that torque. So resisting torque, I am taking that in the two way, like resisting torque by the cylindrical surface and resisting torque by the top and bottom sides. So by resisting torque by the cylindrical surface, I am taking as a T1, and cylindrical torque or resisting torque by the top and bottom shear surface we are taking as a T2. So whatever the total torque we are applying, that is T, will be equal to the T1 plus T2. That will be equal to the T1 plus T2. So let's calculate the first, the T1, that is resisting torque on the sides, and side is the cylindrical surface. And what is the side? Sides is a cylindrical surface. So we can calculate torque, that will be equal to the resisting force into radial distance. Resisting force, that is F, into radial distance, that is P. So we can calculate T1. S is the shear strength or shear stress, okay. So that will be constant. So S, and we will to get the resisting force, we will calculate the shear. We will calculate the shear strength into the shearing area, your shear surface area. So what will be the shear surface area when we are calculating, when we are working on the cylindrical surface? What will be the shear surface area? So for the cylindrical surface, we can write pi d h. Pi d will be periphery, or multiply with the h, we will get the cylindrical surface. So we can write S into pi dh into d by 2. D by 2 is the radial distance. D by 2 is the radial distance. So now we have the T1. Let's go for the calculate the T2. And T2 is the resisting torque on the top and bottom sides. Resisting torque on the top and bottom sides. Again T2 will be equal to the resisting force into the radial distance. But problem is this in this case. In this case, the surface, cylindrical surface, is not at a constant radial distance. It is varying, because now we are going to calculate the whatever the torque, resisting torque on the side, on the top and bottom sides. So on the bottom side, because the we are applying the torque according to the vertical axis. So through the vertical axis, radial distance is not constant when you are considering the when you are considering the top and bottom shear surface. So what we will do, we will take a small surface or small a ring, that is radial distance is r from the center, and their thickness is dr. Dr is the thickness, means very small thickness, very small thickness. So we can write d2. So we are calculating the resisting torque for that a small element, that a small ring, right? So we can write T2 is equal to df. Df is the small resisting force into P. P is the radial distance. Again we can write T2 is equal to, अब df we will write S. S will be constant. S into the, what are the area of this ring? What are the area of this small element? So we can write pi 2 pi r. 2 pi r is the periphery, length of periphery into the thickness. Thickness is dr. So we can write 2 pi r into dr and into r. Into r is the radial distance. Then we can calculate. So we can write T2 is equal to S into 2 pi r square into dr. Right. Or we can by integration we can calculate. See, why we are multiplying by 2? Because we are working on the bottom. So now we are calculating the T2 resisting torque both on the top and bottom. So that whatever the that resisting torque we are getting from the bottom, it will be same on the top. So top and bottom will be same. So that's why we are multiplying by 2. So by the integration, by solving this integration, you can get the T2 is equal to pi s into dq divided by 6. S, where S is the shear strength of a soil and d is the diameter of steel blade. So again we can write total resisting torque, that will be equal to T1 plus T2. So that we write S pi dh into d by 2 plus pi s dq by 6. Are you getting my point? Okay. So by taking the common of pi s, we can write T is equal to, that applied torque or resisting torque is equal to pi s into d square h by 2 plus dq by 6. So we can write shear strength is equal to T divided by pi into d square by h, d square h by 2 plus dq by 6. So by using this formula, we can calculate the undrained shear strength of a soil by conducting the Vane shear test, where T is the applied torque, and that we will take the value of by reading the scale, okay, where the D is the diameter of stainless steel blade, H is the vertical height, or generally 2 times of diameter. So by using this formula, we can calculate the undrained shear strength of a soil. Again, another important thing, if the top of the vane is above the soil surface and the depth of the vane shear inside the sample is H1. See, in the we have derived a formula, but that condition was we have inserted the steel blade such that the top of the steel blade should be at a depth of 10 to 20 mm below the surface of soil specimen. So that's why we have counted both the bottom and cylindrical and the top surfaces participating in the torque resisting, participating in this shear phenomena. But now case is different. The top surface is not inside the soil specimen, means the top surface is not participating, and the total height is also not participating. The height of H1 is participating. So the formula will be changed, or that you can derive also. I'm writing the formula, but that you can find out by the proper derivation. So that will be equal to S is equal to T divided by pi into d square h1 divided by 2 plus dq divided by 12. So in the most of cases, generally you will see that the question will say that both top and bottom part is participating in the soil shear strength phenomena. So when the both top and bottom will participate, then you will use the formula is dq by 6. When the question will say only the bottom part is participated in the shear phenomena, then in that case you will write the formula, and in the formula you will just dq by 12. So at the place of 6 it will be a 12. And there is a third case where the top surface is not participating in the shear phenomena, also the total height is not participating, only the h1. So in that case you can use this formula, right? I think there is no confusion. So this is the shear stress distribution on the steel blade. So that is important, you can see. So this is not a shear stress distribution, this is a steel blade mentioned in the figure. So I am going to discuss the shear stress distribution on the steel blades. So you can see on the side of the steel blade, the shear stress is constant throughout the height because there is a S into 2 pi dh. So where d and h is constant, so whatever the resisting force will be constant. But in the case of top and bottom, so in the formula wise you can see S into 2 pi r dr. So r is varying. At the center of steel blade, r is 0. So the value will be 0 of shear resisting force, the value will be 0. Or on the periphery, the r is maximum. So you can see from the center to periphery that shear strength or shear stress is increasing linearly. So this is the distribution of shear stress distribution on the steel plate, or you can say there is a resisting force distribution on the steel plates, right? So now I am going to discuss some of the numerical problem. So the first numerical problem we have: a fill vane shear testing instrument as shown in the figure was inserted completely into the deposit of soft saturated silt clay with the vane rod vertical such that top of the blades were 500 mm below the ground surface. Upon application of rapidly increasing torque about the vane rod, the soil was found to fail when the torque reached 4.6 Newton meter. So 4.6 Newton meter will be equal to T, applied torque. At this point of time, the soil specimen get failed. Assuming mobilization of undrained shear strength on all failure surface to be uniform. So before the derivation of the formula, we have taken the same assumption. So it means we can apply that formula. In other questions, suppose the question are not saying about all this data, so directly you can apply that formula. If they said that about that, they are using some Vane shear test and suppose some data they have got on the basis of Vane shear test apparatus, so you can apply that formula directly. So there is no issue. Okay, and the resisting mobilized on the surface of the vane rod to be negligible. That is also the assumption. So what would be the peak undrained shear strength? So we have to calculate S. So we have the T. So we have to find the D and H. So that D and H you can get the value by seeing this figure. So the height is mentioned 100 mm and diameter is mentioned 50 mm. So in this case also height is 2 times of the diameter. We can write H is equal to 2D. So we have all the formula: D 50 mm, H 100 mm and T 4.6 Newton meter. So you have to take care of this unit because D and H you have this written in the mm. So better this you can write in the terms of meter, because T is given, torque is given in the terms of Newton meter. So either you can make the Newton mm, or you can make the do the calculation in the terms of meter. So shear failure will occur at the both top and bottom. It means in this case both top and bottom parts are participating in the shear phenomena, right? Because this in the question it is mentioned the vertical rod such that the top of the blades were 500 mm below the ground surface. If 500 below the ground surface, it means the rod, the steel rod is 400 mm inside the soil specimen. It means top and bottom surface of this steel plate are both participating in the soil phenomena, right? So there is no confusion. So we can apply directly. We can apply the formula: H is equal to T by pi d square H by 2 plus dq by 6. So we have all these value T, D, H. So by putting all these value in this equation, we can get the shear strength, that is 10040 Newton per meter square, right? So in this test only just remember these two formula, like in the case of when both top and bottom part, top part is participating in the soil phenomena, the formula will be this dq by 6. If top part of the steel blade is not participating in the shear phenomena, in that case that formula will be same except dq by 12. In the place of 6 it will be 12, right? So these are the reference that I have taken. So in the next lecture I am going to discuss the numerical problems, whatever all the numerical problems from this shear strength of a soil. So I will discuss some of the gate problems, I will discuss some of the engineering services examination problem, and then I will shift in the second unit, that is the stability of slope, right? Okay. I will upload one more lecture from this unit, and in that lecture I will discuss only the numerical problem, and then I will give you one assignment that is based on the unconfined compression test. So there is an observation that I have taken during the unconfined compression test. So I will give you the assignment. Okay, thank you.